With this video, theoretical background of single loop and multi-loop control will be briefly described. This slide shows the red thread of the control education at the University of Ljubljana Faculty of Electrical Engineering. When we implement a control application, we usually follow to this concept, which can be described with three clouds. Namely, we have a simulation environment. We usually use MATLAB Simulink or Daimola Modelica. Then, of course, we must have a target computer, PLC, industrial controller, or something like that. And of course, we have a real process which has to be controlled. At the first stage, we use the simulation environment. Models of a control scheme and of a real system must be, of course, available. In the second phase, we connect simulator and real process. So this means that this part has already to work in real time. The control scheme is in the simulation environment and is connected to the real process. In the third phase, we connect simulator with the target computer, of course, in real time. Model of the real system is in the simulation environment, and of course, the target computer, PLC, or industrial controller must in real time control the simulated process. If first, second, and third phase work appropriately, then we can go in final implementation. This is the phase 4, where target computer controls the real process. Our focus in the control education is also based on hands-on experiments with laboratory setups. We have several laboratory setups. One is 3 tanks hydraulic system. We have several mobile systems. A must of the equipment is also inverted pendulum, very appropriate for more sophisticated control studies. And we have also the motor generator system. With this slide, the basic control approach, the single loop control, will be briefly presented. In most control applications, single loop control systems are sufficient. What we have to do is to set the optimal values of their parameters, which assure the best possible control. This is a block scheme of a single loop control. Single loop means that we have one feedback loop. In this block scheme, we can see the controller, we can see the plant. We have 2 input signals. One is reference or the desired signal, another is the disturbance signal. And what we control in the scheme is this controlled variable. This controlled variable is measured. It is compared with the reference value. The error is calculated, and on the basis of this error, the PID controller calculates the control variable which controls the plant. As we introduce 2 inputs, reference and disturbance, we also talk about 2 controller modes, about reference tracking mode and about disturbance rejection mode. It is important to talk about 2 modes because the settings of the PID controller are different for the reference tracking mode and for the disturbance rejection mode. However, the single loop control is not successful in the case of the system with significant disturbances or with large time constants. So we have additional solutions. This solution is multi-loop control. We can talk about two possible approaches. Each approach has additional control loops. One approach is so-called feed-forward compensation. It is a kind of open-loop solution. It works on the way that a disturbance is taken into account before it significantly influences the controlled signal. The other approach is cascade control. This is the feedback control solution, and it means the introduction of auxiliary loop and auxiliary controlled variable. Time delay compensation and effective disturbance rejection is achieved with both approaches. This is the block scheme of the feed-forward compensation. So, in this approach, we are considering the disturbance. So, the reference signal is in this consideration not so important. The disturbance influences the controlled variable through this path. And if the disturbance can be measured, we measure it and introduce a new path. This is the path of feed-forward compensation. This measurement is gained by a constant value. This is so-called proportional feed-forward compensation, and this signal influences the controlled variable. So the basic idea is that the influence through this path and this path are in this point somehow compensated as much as possible. Of course, the ideal situation would be that the influence of this path and this path are completely compensated, but it is of course not possible. At least it cannot be done on a perfect way. Another multi-loop solution is the cascade control. In this approach, we generate additional controlled variable or controlled point, and we introduce so-called auxiliary control loop and auxiliary controller. The auxiliary controller is usually a simple one, P controller. But this part is slightly the same as in single loop control, so this is in this case so-called primary controller, PID with proportional part, integral part, and derivative part. And such solution is extremely effective if the disturbance influences the control system before this measurement point, before this auxiliary controlled variable. And it is also very efficient if the big delays of the process are concentrated in this part. In these cases, the auxiliary control loop eliminates the influence of the disturbance significantly, but it also reduces the effects of large time delays which are in this part.